All right, well, we're going to wrap up part one with this lecture, and we're going to be looking at the Vesper theory, molecular shape, and then we'll end this part talking about intermolecular forces and how that affects the physical properties of organic compounds. Now, I will say I believe that Vesper theory is covered in general chemistry, and so well, probably a good deal of what I say is not going to be new. We're just going to be applying it to organic molecules. So, and the great thing about the molecular shape is that all of the extensive ones that you went into with general chemistry, we typically don't focus on those in OChem. You'll see that there's very few shapes that we actually concern ourselves with. Um, so the first one that I want to take a look at is in compounds that have four regions of electron density. Now, just to relate this to what we've talked about previously, these are sp3 hybridized atoms because they have four regions of density. Now, depending on whether those regions are lone pairs or not, will affect the shape slightly as well as the bond angle. But if all of those regions of density involve bonding electrons, so you have four single bonds, like in the case of CH4 here, then we designate that as the tetrahedral shape. And the bond angle will be fairly close to about 109 degrees. Now, if we go to a molecule like, for example, ammonia, ammonia still has four regions of electron density. And you would think, well, we should call that tetrahedral. The problem is that lone pairs occupy more space. And the Vesper theory will predict that that should cause the atoms to want to spread out more because they occupy more space. So the bond angles here in ammonia are a little less than 109. So we designate that with a slightly different shape. We call it trigonal bipyramidal. And it's slightly more drastic when you have a molecule that's got two lone pairs, like, for example, water. So the shape for water, we call that bent. And the bond angle is a little bit lower than 109, and also lower than the trigonal bipyramidal shape. So those are the three that we'll concern ourselves with when something has four regions of electron density. Now, when we go to three regions, we don't have a lot of subcategories. Three regions of electron density is the trigonal planar shape. Now here, for example, you see boron trifluoride. To make this a little bit more into our organic chemistry, we can look at this compound, contains carbon and hydrogen. And the thing to relate shape to hybridization is that sp2 hybridized atoms have a trigonal planar shape. And then finally, for two regions of electron density, so these are atoms that are sp hybridized, the shape is linear, has a bond angle of 180 degrees. So we've seen some examples of that already in lectures, past lectures. So these carbon atoms here each have two regions of electron density around them. They're both sp hybridized and so their shape is linear. So let's just get a little bit of practice with this and then we'll move on. So use Vesper theory to predict the geometry of each structure. So like hybridization, this is just as simple as counting electron density around an atom. So in letter A here, this boron atom has four regions of electron density. They are all bonding electrons. So we would call that tetrahedral. In the next one, there's 3 regions of density. And so we just kind of default to trigonal plane. Now, if we look at C, we got a nitrogen there. Now, in the example I did before, when we saw nitrogen, that was like trigonal bipyramidal. But again, it doesn't really matter about the atom. It matters what kind of regions are they. Here, around that nitrogen, it's 4 sets of bonding electrons. There's no lone pairs on that nitrogen. And so we would call that tetrahedral. And then the last example, again, 4 regions of electron density. All 4 of them are bonding electrons, so that is tetrahedral as well. Now, closely related to molecular shape, you have to be able to know molecular shape in order to look at the next molecular property, and that deals with polarity. Now, again, polarity is a concept that's covered in general chemistry, especially when you are talking about polar bonds versus non-polar bonds. So I'm assuming you're a master's at recognizing polar versus non-polar bonds. We're going to take that a step further and use that concept to see if compounds, entire molecules, can be polar or non-polar. Now, to determine if a molecule itself is polar, it has to have 2 properties. Both of these have to exist. Number 1, it has to have polar bonds. Now, a little side note with OChem, carbon-carbon bonds are very common. Carbon-carbon bonds are never polar. Carbon-hydrogen bonds are very common. Even though there is a slight difference in electronegativity, we do not treat carbon-hydrogen bonds as polar. So that's the first qualification. It has to have polar bonds. And then it has to have a net dipole moment. That's just a fancy way of saying the polar bonds don't cancel each other out. You don't have one going directly to the right and then one directly to the left, and they have the same atoms. Those cancel each other out, and there's no net direction in polarity. So let's apply those 2 concepts, those 2 rules, to look and determine if these compounds are polar or not, or if they have what we call a net dipole moment. Sometimes this might, in the beginning, require you to draw out the Lewis structures. So if we look at the first example here, let's just draw and I'm trying to make it as tetrahedral as possible here. So these are not at 180 degrees. I'm sorry, 90 degrees to each other. Now, the carbon-hydrogen bonds, we are not going to treat those as polar. But carbon-chlorine bond is a very polar bond. Chlorine's very electronegative. And so there's a net direction of polarity in this direction. So we would say that this compound is polar. Now, if we look at CCl4, carbon-chlorine bond, as we just said in the last problem, are polar. The problem we run into is that all of these exactly the same polar bonds cancel each other out. There is no net direction, or I'll say no net dipole moment. So this would be a non-polar compound. Now, the last one here, when kind of, start looking at, we don't necessarily have to draw a Lewis structure. It might help, but if we assume that the carbons are attached to each other, the oxygen is attached to that second carbon, then all of this here is not going to be polar because it's carbon-carbon bonded, it's hydrogens bonded to carbon, but we got a carbon-oxygen bond here. And that is a polar bond. And so there's that net direction of polarity towards the oxygen. So this would be a polar compound. Now, another way that we can visualize this, and this is more kind of like a nice picture way, something that a computer will help calculate for us, is we use something called an electrostatic potential map. And that's just kind of a fancy word for like we're using colors to tell you where the polarity is at if there's a net dipole moment. And so here, for example, we're using water. And the idea is that the more bright color is, like when I say bright, like we're going from orange to reddish, that indicates high electron density. And the more warmer the color is, like blue, green, going from like green to blue, that indicates a region of low electron density. And if we just look at the structure of water itself, we can see why there is that separation of polarity, is because oxygen's more electronegative than hydrogen. And so it's drawing electrons towards it. And so there's that net dipole moment towards the oxygen. Now, if we look at the second diagram, here we see carbon dioxide. Carbon dioxide has polar bonds in it. A carbon-oxygen bond, just like in the first problem, is polar. But we can see that there's direction of polarity towards this oxygen and an equal direction of polarity towards the other oxygen. They cancel each other out, even though, and you can kind of see there's an equal electron density on one side as there is on the other. And it cancels each other out. That's why carbon dioxide is non-polar. Now, let's get a little bit more practice. So do these compounds exhibit a molecular dipole moment? Meaning, are they polar? If so, indicate the direction of the net molecular dipole moment. So with A, what we're going to start off is by drawing a Lewis structure. And we're going to try to draw it as three-dimensional as possible. So H, and then Cl, Cl, Cl. It is tetrahedral, so you have to remember that. And carbon-hydrogen bond, yes, there is a slight difference in electronegativity, but we don't really count that as like polar. It is nowhere near as polar as a carbon-chlorine bond. So those three arrows do not cancel each other out. In fact, if we're going to draw kind of a net direction of polarity, we might draw it something like this. But there's a net direction of polarity for letter A. Now, let's take a look at B. It's kind of deceptive the way it's drawn. If you just decide to do B like this and not consider three-dimensionality, you look at that and say, oh, well, there's this and then there's this. So those cancel each other out. Okay, you can't look at it like that. Remember that oxygen in the middle there is sp3 hybridized. We're going to draw it in that manner. And so now that's kind of a little bit of a better perspective. Since the linear shape of, or not linear shape, the Vesper theory shape around it says it's bent. Now it's a little bit easier to see, okay, yeah, there should be a net direction of polarity towards this direction. And that would make it polar. Now let's look at E, and I'm going to use the structure right here on E rather than redrawing it. It's already kind of drawn as a Lewis structure. And we're going to ignore it, all the carbon-carbon bonds, the carbon-hydrogen bonds, and just look at the carbon-oxygen bond, because that's where the polar bonds are. Again, both of them are kind of going in the upward direction. There's nothing canceling them out. So the net direction of polarity is towards that oxygen. Now I want you to take a close look at F. Very similar structure, except Notice what happens here. We have an arrow going upward and to the right, an arrow going upward to the left. But then we have an arrow here going downward right and downward left. Those two on the bottom cancel out the two on the top. There is no net dipole moment. Now let's take a look. I and J are very similar, but I want you to kind of take a look at the slightly how different they are. Because in I, again, we're focused on the carbon and the chlorine polar bonds. You have one going like upward to the left, one upward to the right. There's a net direction of polarity in towards like the middle of those chlorines. So that would be polar. Look how that contrasts with J though. In J, you have one kind of going upward and to the right, and then you have one going downward and to the left to an equal degree. Those two directions of polarity cancel each other out. So there's no net dipole moment. Now, the last thing we're going to look at in this part is the role intermolecular forces play on the physical properties of compounds. So I'm going to start off with something known as London dispersion forces. These are also known as van der Waals interactions. Um, and so the London dispersion forces are like the weakest of all the intermolecular forces. And when we talk about intermolecular, we're looking at how does one molecule interact with another. London dispersion forces are temporary attractions when two molecules get close. And here's what I mean by that. Let's look at pentane here. Pentane's got 5 carbons in it. And I want you to look at these electrostatic potential maps here. As one pentane molecule gets close to the second one, what happens is those electrons between them don't like to get close together because electrons don't like to be close. So literally what happens is as they get close, the electrons on this side of the molecule are like, hey, we gotta bug out for a little bit. So they're going to kind of force their way over to the other side. And that leaves this region over here slightly positive. Well, what is attracted to positive? Negative stuff. So because there's a region of positive, this region of negative over here starts to develop. And you have this kind of temporary interaction as long as those two molecules are close together. Now, one of the things that maximizes these interactions is molecular weight. So take a look at these 3 compounds here, butane, pentane, and hexane. I want you to note their boiling points. I don't want you to memorize them, but notice they get higher as you add carbons to the molecule. So the boiling point increases as molecular weight increases. The reason for that is there are more points for the molecule to associate the longer the chain is. Now, something interesting that I want you to know is what happens when you're looking at constitutional isomers. So here are the constitutional isomers of pentane. We did this example a few lectures ago. Even though they have the same formula, look at the boiling points. So as there is more branching, and when I say branching, if you look at pentane, it's 5 carbons in a row. If you look at 2-methylbutane here, You got four carbons in a row and one guy hanging off here. If you look at 2,2-dimethylpropane, you got like three carbons in a row, and you got one hanging off here and one hanging off here. So even though they all have the same formula, their boiling points are different because the boiling point decreases as branching increases. And again, this comes when you are comparing constitutional isomers. It gets a little weird if you're trying to compare a branched compound with another compound that's straight, but it has fewer carbons. Like it gets very difficult to try to judge that. You almost have to have your boiling points memorized, which I don't have them memorized, and I don't expect you to. So if you were ever going to compare, it always would be between constitutional isomers. Now, the next intermolecular force that is important to know about is dipole-dipole interactions. These occur between polar molecules. Okay. You will not see these in polar compounds. I'm sorry, non-polar. So one thing to kind of keep in your mind, non-polar compounds like these here, the only force of attraction they have are London dispersion forces. Now, polar compounds have those. They have London dispersion forces, but they also have another intermolecular force, and that's when the opposite poles are attracted of one molecule are attracted to another. So take a look at acetone here. Acetone has a net direction of polarity towards the oxygen, and that makes this side partially negative and this side partially positive. Well, when one acetone molecule interacts with another, that negative end is attracted to the positive end. And then the negative end of that one is attracted to the positive end of the next one, and so on and so forth. Now, if we compare that to isobutylene here, isobutylene is nonpolar. It does not have any dipole moments. There's no negative end, there's no positive end. So this compound only has London dispersion forces. Acetone has London dispersion and dipole-dipole interactions. So because it has more intermolecular forces, look at its boiling point compared to isobutylene. Isobutylene is like in the negative. The boiling point of acetone is 56 degrees Celsius because it has more intermolecular forces. And then the last one that you should know is hydrogen bonding. Hydrogen bonding is a special type of dipole-dipole interaction that occurs when hydrogen is bonded to a highly electronegative atom. And that's usually where you see that in OChem is usually oxygen or nitrogen. As an example of this, let's compare ethanol here to methoxymethane. Ethanol has a hydrogen bonded to an oxygen. Methoxymethane has an oxygen in it, but not a hydrogen attached to it. And look at the drastic difference in their boiling points. Ethanol is like 78, methoxymethane is below 0. So how does this hydrogen bonding work? The hydrogen attached to an oxygen of one molecule is attracted to the oxygen of the second molecule in a dipole-dipole fashion. And so ethanol can do this, methoxymethane cannot. So, and we'll just kind of let's just put this all into perspective. Both compounds have London dispersion forces. They both have dipole-dipole interactions because they're both polar, but only ethanol can hydrogen bond. And so that increases the boiling point of ethanol even more. So let's do a few problems, and then that will be it for part one. So for each of these pair molecules, we're going to identify the compound with the higher boiling point and justify our choice. So we're going to look and see what the difference is between these. So with A, both have the same molecular formula, right? 6 carbons, an oxygen, and 12 hydrogens, right? 3, 6, 9, 12. I'm sorry, 14 hydrogens each. So what's the main difference between them? Well, this one, is linear, not molecular shape, but it's like in a straight line is what I mean. And this one is branched. So these are constitutional isomers. The rule of thumb between constitutional isomers is that the branched one will have a lower boiling point. The one that is straighter with less branching will have the higher boiling point. Now, if we look at B, we can see that they don't have the same formula. B has 5 carbons, so C5H10. This is C6H12. They don't have, so we're not comparing constitutional isomers. So what we're going to compare is molecular weight. So since this one has a higher molecular weight, it's got more carbons in it, it's going to have a higher boiling point. Now let's take a look at C. With C, we're comparing constitutional isomers. Both of them have the same formula, C4H10O. Both of them are polar, but if you look at the one on the right can hydrogen bond. And so it's going to have the higher boiling point. And then finally with D, we take a look again. So the formula, they both have the same formula, C4H10O. Now both of them have an OH group. So they both can hydrogen bond. They're both polar. What's the only other way that we can tell which compound have the higher boiling point? Well, since we're dealing with constitutional isomers, here now we're going to compare that one is branched and the other is not. So the unbranched chain, the compound with the unbranched chain is going to have a higher boiling point than the one with the branched chain. So that will pretty much conclude part one. Those are the lectures that you should be getting through for this week. So I highly recommend as soon as you can start on the problem set so that if you are running into issues, you can come to office hours and ask questions. So that will be it.